So in our laboratory, we work on nanoporous covalent organic polymers in short cups for CO2 capture. So first of all, why do we do CO2 capture? And the main reason is the economy of CO2 capture is so unfitting to current scenarios. And we know all these countries are trying to capture CO2 and store it down in the geological reservoirs. But in fact, we know that there are so many challenges with all those. But if you break down what cost is associated in what part of the CCS scenarios, like carbon capture and storage, then we realize that carbon capture is the biggest portion of the cost for CO2 capture. And transport or storage is not that expensive, but if we could cut it down to $18 per metric ton from the $38, then we can pull it down to $30 per ton CO2 avoided, and this will make it more affordable to implement in larger scales. Still, it's not free, so that's one of the biggest problems of CO2 capture. The CO2 that you are capturing will cost you, and that's going to turn into more fossil fuel extraction and more profits from other sources, and that's an unending story. So if you think about what would be the best in terms of CO2 capturing and recycling and storing, so we cannot think anything other than a natural cycle, because the living beings like us are dependent on these organisms like plants. So this is the natural way of fixing the CO2 problem. And in this scenario, we would be putting a magic powder down underneath the plants and the trees, and then we shine our light onto it. Hopefully it desorbs the CO2 during the sunlight or heat, which we call a stimulant, and it turns into CO2, free CO2, and that enhances the photosynthesis around the plant. And then later we, when it's nighttime, when it's cold, no sunlight, not as much of photosynthesis or any biological synthesis is going on, so CO2 goes back from the air to the magic powder down at the bottom of the tree. And then the adsorbent has its own CO2, and the cycle restarts the next day. So this would be the ideal scenario for CO2 capture. But the problem is presence of CO2 in the air is not that much, so we don't have much CO2 in the air. And also there's no such magic powder. So those two problems are keeping us from doing this, but I think ultimately we will arrive in such solution. So what's more feasible is the power plant exhaust fumes, which is what we make our energy from, or produce our energy from, the coal, the natural gas, the petroleum. In that we have different scenarios of the CO2 capturing. And the most likely one is the post-combustion capture, because this is already in place. We always burn fossil fuel to make power and heat, and the flue gas goes to the atmosphere usually without CO2 scrubbing. But we could attach a CO2 separator. And the things we need to consider are the temperature of the exhaust fume is not room temperature, it's hotter than that. And pressures are low compared to other processes. Nitrogen is high amounts present, and CO2 is much higher quantities than air. It's 15%, even 10% is very high compared to air presence. And there is just water, steam or vapor coming out of the flue gas, and that is the biggest showstopper for many different emerging sorbents, and I will tell you in a little bit. So the other option is not trying to mix up the CO2 with anything else. That's why the gasification is in place. The fuel is gasified with oxygen from air, which is separated. So there's another separation you need to do here as well. But then you produce the syngas or hydrogen in pure form, hopefully, and then you burn that to generate power or heat. And this gives you, to get rid of CO2 before it mixes up with other gases from air. And then oxy-fuel is something that you burn the CO2, you burn the fossil fuel directly with pure oxygen, and then you produce almost pure CO2 and water as well. So let's also see the pre-combustion conditions require 4 degrees Celsius, well, it emits 4 degrees Celsius of the flue gas, and the pressure is very high, 30 bar, and it's 60-some% hydrogen and 30-some% carbon dioxide. So which means 1 to 2 ratio of hydrogen versus CO2, and that means 10 bar partial pressure of CO2 in that pre-combustion feed. In oxy-fuel conditions, it's almost pure CO2, so we don't need to do anything really on this, except recondensing water and then storing CO2 away. So, in what conditions? We've seen 3 different conditions: post-combustion, pre-combustion, oxy-fuel. Oxy-fuel doesn't need capturing CO2. So, what are the differences between post-combustion and pre-combustion? And the post-combustion, as you remember, is a low-pressure system, meaning that it's over here somewhere. This is pressure versus capacity of capturing CO2. And in pre-combustion conditions, we have a very high, and I calculated that, or I talked about that in being at 10 bars at least, possibly more. So it's up here somewhere. In that case, when we see the pressure being really high, a physisorption, physical absorption, gives us what we want if we are at high pressures. But at low pressures, chemical binding is very important because we don't have much physical absorption. So that gives you the idea that what chemistry we should be focusing on, or physics, or blending, in terms of removing CO2 from combustion processes. So, as you can see, post-combustion capture requires chemisorptive materials, very strong binding. But if you're working on pre-combustion, or if you have CO2 at very high pressures, partial pressures, then you don't really need to research on anything particularly strong binding. You just need a cheap solvent, or sorbent in a solid form, which will give you all the capacity you want. So that gives you the idea of what to look for. Because if you are trying to pursue a pre-combustion route and trying to make, we made this very strong binding, CO2 binding material, and we're going to look for pre-combustion conditions, this is not going to fly as much, because at high pressures you don't need strong binding. And Steve Chu, the former Energy Secretary of the United States, has shown in his paper, and this really goes along with the chemisorptive idea, as I just told you. So the adsorbents, usually when you increase the binding energy, which is dictated by the reaction enthalpy of the sorbent plus CO2 gas, is going to increase, of course this is the magnitude, to very high values, in which the rate of binding, kinetics, will also be going high. So this is a linear relationship. And this won't be as ideal, because you're going to be needing a lot more energy to regenerate sorbents if you go this side. So that's why you need to be staying down in reaction enthalpy, but at the same time you want to have a very fast kinetics. You don't want to wait for CO2 to absorb. So these this is the region where you want to be in terms of chemical binding. So this is for post-combustion conditions again. Another very important metric I have to talk to you about is the working capacity. So working capacity is not the capacity you measure when you're taking an isotherm. For example, if you measure an uptake capacity of something from almost vacuum conditions up to 1 bar, you're essentially getting the total capacity from no gas absorbed until saturation. But the problem is when you regenerate that sorbent back down, you don't go to 0 pressure. You go to a normal pressure, like whatever your operation is running on. So this is a pressure swing conditions, pressure swing adsorption, in which we have a high pressure value where you're adsorbing and low pressure value where you're desorbing. So the difference between these two is called the working capacity. The same thing with the temperature swing adsorption. T2 versus T1. T2 would be desorption, T1 is adsorption at that time. So you have to make the difference between those two values so that that's your working capacity. In very strong binding structures, the pressure values won't matter. You will not have any working capacity, such as extremely microporous crystalline materials like mouths or other very highly strongly binding like silica amines. You will have hard time getting a positive working capacity for pressure swing conditions. But temperature swing, of course, you can heat up too much the sorbent, so you get all the CO2 out. So in that case, silica amines would be a favorable target. So this is very important to know, because if you don't have a positive working capacity, there's no way you can talk about a CO2 solvent. And let's look into the working capacity per regeneration energy. These are great graphs from this paper, and if you want to take a look at it, you should go look at it, by Professor Zaw at Texas A&M University. So the MEA actually goes a little bit high in working capacity, not even reaching 1 millimole, which is 4% CO2 uptake. At the desorption temperature of 120, which is normally the industrial conditions. So, and there's 0, and certain sorbents that Professor Zaw, Joe Zaw, produced in his laboratory are not reaching to beyond 2 millimoles until after reaching to 120. So this is a very informative graph, and if you have to do similar graphs, you should look into their paper and try to reproduce their data. And another important metric is the working capacity per energy. So how much energy you need to use how much millimoles you can get per kilojoules you're spending. And of course, if your desorption temperature increases, you're spending a lot of heat to regenerate. So some of the emerging sorbents they have are going to go to lower in terms of higher the regeneration conditions. So there's always a sweet spot, and that's what you could be seeing in your systems. And an energy per gram of materials is MEA probably is the highest energy per gram, because it's energy intensive process anyways. But the other emerging solids are not that energy intensive. And if you chart this working capacity per energy versus working capacity, you want to be up there. The higher millimoles per gram of sorbent, this side, and more CO2 captured per same kilojoule. So you want to be up here somewhere. So that's why one of these structures has given that very high impact. So you need to really understand working capacity and how much energy you have to put in your sorbent to regenerate. So let's look into what industry is using, and that's what we call MEA, I just talked about, which is monoethylenamine. It's a molecule dissolved in water in 20% or 30% amounts. It's a very old technology, but it works beautifully. It's very well. It's a mature technology. There are several plants are using it in various forms, and also new plants are being built, which shows that this technology is the gold standard, and which also tells us that we have not developed something that would be better than this old amine in solution technology. So that's why we are trying to do to capture CO2. Once we have all the CO2 captured, the problem now becomes where do we actually sell? And the first thing we think is the CO2 market, like beverages, like urea, like methanol, and all other things that we can make from CO2. But the scale of this entire CO2 market is only negligible compared to all emissions we have, and this is just 32 gigatons. Now it's more than 40. So CO2 market will not be enough, not even making a dent on CO2 emissions. So there is the problem of what to do with CO2. Of course, that's not the first problem, because the first problem is how do we capture effectively, and once we capture that, then CO2 can be stored underground. Right now they do it for oil wells, and that could continue until a certain time. So let's focus back on the CO2 capture that we're dealing with. So what kinds of pores do we need in a solid system? I think it's obvious to many people already that we need a porous something to replace liquid amines, because porous is easy, it's powder, it's crystal, whatever, and you just put it in columns and you do all your cycles. So what kind of pore do we want? Because CO2 likes micropore. It's a small molecule. It's much smaller than 2 nanometers. It's 3.6 angstrom to be exact. But then only micropores will not be enough because of the diffusive properties, which requires mesopores, intermediate channels, and macropores, the larger channels. It's just like our lungs, where we do respiration. We take in air and then we utilize the oxygen and we desorb CO2 from our bloodstream. So in our lungs we have all kinds of pores, and that really should be the way we approach to this problem. In a solid structure we need to have a variety of these pores. You can call them a nanopore. That's why we call our structures nanoporous. Hopefully we will mean that all these three regimes are covered under the 100 nanometer upper scale. So let's look into what kind of options do we have in terms of porous materials. The good old porous inorganic materials are the ones that you think of first. Zeolites are the most used porous materials in industry for mostly catalysis, cracking, for high-end, and then detergents for in bulk quantities, but low level technology. But zeolites like water more than they like CO2, and that's a problem, because if you look at the post-combustion conditions, you realize there's a lot of water, and you don't want them to really go after the water first, then CO2, because then you would lose a lot of sorbent. So the mesoporous silica or other similar inorganics do not have much capture capacities, and also they're not that easy to make because you need to have a lot of surfactant, although relatively easier compared to many other sorbents. But since zeolites are natural and you can make them in bulk quantities, this looks like a little more advanced material. Which takes us to the even more advanced materials, the hybrid inorganic-organic mixture porous materials. And these are commonly called metal-organic frameworks or covalent organic frameworks. They're based on organic and metal repetition into permanent pore making. But these are crystalline materials. They have great chemical tunability, great crystallinity, but then they're moisture sensitive, they're fragile because they're crystalline. Their organic components do not allow more than 500 degrees Celsius usage, and they're not that cheap. Same thing is true for these boronic esters. These are even more moisture sensitive. That's why these structures are mostly tuned for specialized applications like hydrophobic gas storage like methane or other alkanes or separations. And perhaps some photocatalytic properties would be of use very soon. So these are highly promising emerging materials, but do not do well for CO2 capture. So the frameworks linked with CC bonds are probably more fitting to what we want, and that's why I will lead you to our network polymers discussion. And these are extremely robust. They are CC bonded systems, just like diamond. They're moisture safe, but they're flexible because of the organic backbone. But although, of course, some of the structures are very rigid, so that's why they may not be as flexible as one wishes them to be. But nonetheless, they're more flexible than inorganics and hybrids. They have very high surface areas, of course not as much as the MOFs, but more than the inorganic materials. The problem with most of the initial examples are the lack of chemical specificity, and also being purely organic also means that you cannot heat them way too much. And particularly PPN4 has a very high surface area, actually highest in very stable compounds, like water stable compounds. So that is something to note. And there are other organic-based porous polymeric networks. So this is what I want to introduce, because if you are trying to capture CO2 and all you need is a pore, and network polymers give you that permanent pore, plus all these functionalities, and so many other groups have worked on this. Very high capacities. If you remember, monoethylamine has a working capacity of 1 millimole per gram, so this is 6 total capacity, but nonetheless, you could cycle like 2 millimoles with much easier conditions. And the benzimidazole-linked polymers by Professor El-Kadiri at Virginia Commonwealth University, these are also very exciting materials with high CO2 N2 separation capability and high uptake capacities. And the reason why I'm highlighting these structures is because the network polymers are good old polymers. You can just design from any organic molecule. But then they have very strong covalent bonding to hold them together in case your power plant requires very harsh conditions to capture CO2. And then the flue gas also contains lots of other unwanted gases like sulfur oxides, nitrogen oxides, although they're required to be removed, but there's always a leftover trace amounts coming off. Even mercury comes off. So your structures ideally should not break down immediately, although they will wear out, but they should not break down. And certainly organic compounds have a lot more potential in this context. So when we think about these network polymers, do we even need a pore to capture CO2? And it seems like you don't have to. And these people, Zoe and other co-workers, have shown that this almost non-porous network has uptake capacity of almost 2 millimoles or more, and this is already in par with many high surface area polymers. So this is a very striking example of you could also benefit from chemisorptive behavior with respect to what you want to accomplish. And the amine tethered silica is nowadays is considered as the one that should be used for low temperature because of the failure of other sorbents mainly. So in that you just want a very porous, ideally mesoporous capsule, because you want to put in something in there and you don't want the pore to be blocked. That's why you want to be mesoporous or higher. And that means once you put them in, CO2 capacity goes really high. And with respect to amine loading, you can get even higher, so almost 7 millimoles uptake. And Professor Gianellis at Cornell has shown that you could achieve extremely high uptake capacities in a very short amount of time. So the kinetics is there, and the capacity is there, and these structures are considerably stable. So this is a very promising work, although there are issues with attrition, with cyclability, because too much amine will be sort of turning into liquid amines at some point because of leaching and all other decomposition systems. So we have done a lot of work in terms of looking into CO2 capture with different materials. And obviously we looked into the inorganics first back in the day in 2009, in which a hydrotalcite, which is double-layered hydroxides, if you promote them with potassium carbonate and gallium, you could achieve very high CO2 uptake capacities. And we looked into hydroxyzincite, which is a very, it's a mixed base, mixed carbonate material at very high pressures. And the Prussian blues were tested for different CO2 uptake capacities and even ionic liquids. We've looked into how they will be behaving in terms of the CO2 uptake. And later we looked into how we can simulate or make a similar structure as MEA is, MEA's molecular structure. And it seemed like amidoxim, which is an organic functional group, could be an answer to MEA because of the similar caging property of the amines and OH groups. And we did a study about its activity in molecular forms in this work, and later we put it on the polymers of intrinsic microporosity, which is PIM structures, so that we achieved much higher CO2 uptake capacities. And then we put in other regular polymers, and now we're looking into making MOFs out of these amidoxims. So these taught us the point of functional group development in terms of what we can capture CO2 with. And before we did all that, I mean, amidoxims, we tested, we wanted to make MOFs with them with the hope that it will produce water-resistant CO2 fluid systems. But in a lot of effort that we spent, it did not work out, and it happens to everyone, so we abandoned the goal of making MOFs out of amine oxides. But in return, we looked into commercial MOFs, in which we went up to 250 bars to see whether or not you could see any collapse in the structure. But the collapse we were testing ended up in MOF 5, where we looked into its stability in air, and we saw that the surface area goes down significantly with respect to the time elapsed. So this took me to a position of the fundamentals. Let's see the fundamentals of CO2 capture. And it seems like the porosity and chemistry are very important. Porosity is being what kind of pores should we have, and the chemistry being what kind of binding sites should we have, and this is a PC role. And if you make pores larger, you have better diffusion, so there's no argument about this. But then again, you lose surface area and small pores, so you lose CO2 capacity. So there is a trade-off between diffusion and CO2 capacity if you're playing with the porosities. So once you think about the chemistry, if you add more chemical structures and functional groups, you increase the CO2 capacity. At the same time, the binding energy increases, because that's how you increase the CO2 capacity in the first place. It just binds to more active sites. But then you lose Physisorption, which is good for regeneration, and that's a trade-off. So if you increase binding sites, chemically specific, CO2 specific sites, then you end up binding strongly, and that in turn gives you higher regeneration energy, and that's something you don't want, because we're developing all this because we want to be staying away from high energy costs. So we looked into making our own network polymers, and that we called them covalent organic polymers, the COPs, in which you're essentially taking, and this is all the work of Dr. Asmuk Patel. He was a research assistant professor in our laboratory. And essentially you take a tridentate or more core structure and a divalent linker, and then you end up, mostly basic conditions, you end up with the network. And of course you could do different architectures, different binding modes, so that you end up with 3D systems. So the core, depending on the dimensions of the core and the linker, you end up with the desired three-dimensional systems as you please. So the COPS is a long story. There are lots of options, and you can check our website, porospolymers.com, to look into what structures we have. The first COP we made was a very inexpensive one with relatively high surface area, with good amount of CO2 capture, the same as MEA. So it's a physisorptive system, and it does really well in terms of dry CO2 capture. In COP 3 is a higher surface area, which actually made us to explore further in this network polymers. The CO2 capture was higher, but then it was very stable under high temperature conditions. That's you can go read about that as well. And later we discovered COP 68 and 69 and another 10 structures in which azo-based COPs, we have seen that you can make a very ultra microporous systems, and then you can have a nitrogen phobicity, N2-phobicity concept, which I will introduce you in a moment. And we have also produced trigger-based functionalized porous networks, in which we have very high surface areas and very high CO2 uptake capacities with very high pore volume. So this is very promising if we could make it in large scales. And benzoxazoles, on the other hand, came out to be extremely helpful in terms of making membranes, because the intermediate of this network happens to be soluble in solvents, and this is very promising for many applications. And very recently we've made 109, in which the structure is extremely inexpensive, and that's what we want to sort of introduce to the world in the next round. So the azo-cops, as I told you, were showing very unexpected result, in which the selectivity of CO2 over N2 was increasing by temperature. So as you increase the temperature, selectivity was increasing. So this was not expected in physisorptive systems, because in chemisorptive maybe that could be expected in some levels, but physisorptive systems this is not really expected. But then when we were puzzled and looking for literature support for this, we found that the famous Professor Rao from India had shown in his paper that azo-mouse actually showed more affinity to argon than stilbene does to N2, which showed a distinctive behavior between N2-phobic azo systems and N2-philic stilbene systems. Of course, they did not make a reference to this, but it was a good support for our explanation. So N2-phobicity, therefore, we explained, Professor Zhang, our collaborator, explained that the entropic loss would be greater for N2 as opposed to CO2. So that was the main conclusion of how and why we have N2-phobicity. And once we looked into other linkers, same azo concept with a bunch of amines. So this is the beauty of COPS, where you can make many different variations by just changing the organic linker. We found that azo-cop 10 has given us the highest CO2 N2 separation. And again, as you still see that the adsorption is still in the physisorptive medium, but yet you have extremely high CO2 N2 selectivity. But this is a good way of pushing forward in terms of CO2 N2 separation membranes. So let me step back a little bit and say why COPs are superior to other porous materials. The first thing that comes to mind is the boiling water stability. These are extremely robust systems. They're not affected by water, so they will not degrade over a week of boiling. This is the CO2 uptake versus the polymer, and blue and red is before and after 1 week of boiling. And they have a 3D structure which is extremely reproducible. You can make it in many quantities without any loss. Morphology is also mostly spherical, or at least grains of micron sizes, which helps in terms of moving in a fluidized bed system. And the thermal stability is extremely high. For example, up to 400 degrees Celsius, there's no loss in the structure. This is air. So organic structures are usually not that stable, but as you can see, it's extremely stable systems. So let's continue on looking into some of the COPs that I mentioned. And the benzoxazoles, as we found, could be made into processable pre-polymer, which is very unique, which is not commonly expected or observed in these structures. And once we cast the pre-polymer from solution, we can cure it into a film, like in a membrane, which could be used as a gas selective membrane. And the applications are underway with collaborations. And then we took the same concept to amidoxamated triethylamidoxam, and we made benzoxazoles. But of course, the direct reaction did not produce anything. That's why we had to go through the silylation, and we ended up forming our network polymers oxazole cops and published it earlier this year. So this is pretty much what the silylation route has given us. Previously, impossible systems like oxodiazole has been made through the system. So what else is important in CO2 capture? And as I said earlier in post-combustion capture definition, CO2 has a big issue with water presence. And in many physisorptive systems like zeolites and other structures, water is competing with CO2, and that's why we cannot use them as often as we want. But then in amines and other chemisorptive systems, you have cooperative binding, where they collectively bind to amines. And we have seen this in a system of COP19 where we added amines to the structure, and we have increased the flue gas condition 0.15 bar. This is dry capture at 0 degrees Celsius, from 0.93 millimole to 1.5, almost doubling the amount, with the selectivity going very high. But then when we tried the actual flue gas conditions, we reached almost 10%. So this is in 2 minutes we have more than 2 millimoles capture capacity, and as opposed to 1.5. And this is also warm conditions at very high flow rate with lots of water presence. So in a way, this structure 97 has given us the proof that cooperative binding can be realized in COP systems if we just added amine functionalities. And once we did the cycling for at least 10 times, we have not seen any degradation of the CO2 capture capacity. And other than that, we also looked into chemically attaching amines to COP surfaces, because previously we have only experimented loading amines physically to the pores. But we also looked into, which is still unpublished, the amine grafting onto the surface. And we've seen in 115, we have taken from a physisorptive nature all the way to very chemisorptive behavior with a lot of hysteresis. So BCD is the ones that contains more amines. What's more striking is the increase in heat of adsorption, in which usually there's no increase with the increase of amine, but we've discovered that CO2 capture can be realized, and heat of adsorption can be tuned by varying the amine length into much larger amines. So this is an exciting data for us. And finally, we have worked on forming chemisorptive sites inside COPs by turning nitrile groups into amines, and we have succeeded in large spherical systems, and also our CO2 capture capacity has become extremely chemisorptive. So this is a work in progress, but very, very promising. So with that, I'd like to thank you for your attention, and you can go and check out our websites. And these are our team members. This is Dr. Patel, who has done most of the work. And our collaborators, we're very thankful for them, and our funding agencies. And thank you for listening, and I'll see you next time.